Welcome to Chapter 1, Section 1 for Math 330, Differential Equations and Mathematical Models. So, what are the three principal goals for differential equations? Goal number one is to discover the differential equation that describes a specific physical situation, to find either exactly or approximately the appropriate solution for that equation, and then to interpret the solution that is found. Big question is, what is a differential equation? An equation relating an unknown function and one or more of its derivatives. So this is a differential equation. It's actually a nonlinear differential equation. Since the y is squared, since y is the dependent variable and x is the independent variable, the y squared makes this a nonlinear differential equation. Here's a second order actual linear differential equation right here. Another type of differential equation is called Newton's law of cooling, and here is the differential equation right here, where k and a are both constants. A solution to that differential equation is this. Now this predicts the temperature of an object that is being cooled, and the temperature surrounding the object is always this constant A. So a cup of coffee that's cooling off, sitting in a room, or a can of Coke that is warming up. But in this case, if it was warming up, this would be a positive instead of negative. But in this case, it's cooling. We're trying to cool off a hot object while it's being surrounded by a temperature that is lower than the object itself. So the way we solve this is we're going to substitute this back into the differential equation. So I've taken my solution for the temperature and put it back in here, where it's right up here in the derivative. And then I've taken my solution for the temperature and put it back right in here, and I get this. So we're going to do some math. I have a and a minus a, so those are going to go to 0. And here I'm going to take its derivative, but this is going to be a derivative of a constant, which is 0. And then I'm going to get the derivative of this. Well, a0, the t0 is a constant also. Basically the initial temperature of the system or object. And that will factor out front, and then I'll take the derivative of the exponential, which is the exponential times the derivative of the exponential, which will just be minus k. And if I do that, I get this system both on left and right, and then so this is 0, and I got the left-hand side is equal to the right-hand side, so this proves that this t here is a solution for Newton's law of cooling. So another differential equation is called Torricelli's law. What is Torricelli's law? It describes the volume of a container as the volume remaining of a fluid in a container as it drains through a hole of radius y. And so this is Torricelli's law, and it predicts, and again, k is just a constant based on the system. And I'm going to claim that this v of y here describes the solution to the system, and where this c is a constant. And so what I'm going to do is I'm going to take that and I'm going to plug it back into here, because that's what v is right there. And then I'm going to take its derivative, and I get this. Well, y to the 1/2 power is the same thing as the square root. So the left-hand side is equal to the right-hand side, and this v of y is the solution to Torricelli's law. If it wasn't, then that would not be a solution to Torricelli's law. The next one is a population model, trying to predict the population or a growing population of a particular kind, and this time kind right here, an exponential growth population, so a population with unlimited resources to draw on. So this is the differential equation that predicts that, where k is a constant, again. And so what I'm going to claim is this is the solution to that differential equation where P0 is the initial population we start at t equals 0. And I'm going to take that, I'm going to plug that back in for both p's here. So I'll put it here and I'll put it here. I need to take the derivative of this side. And if I do take the derivative, I get this. And this makes the left-hand side of the equation equal to the right-hand side of the equation. K's will cancel, everything cancels. And we get 1 equals 1. And it is a solution to the population model. And then, so the idea here is to use math to model physical systems, and so we get mathematical models. And the idea here is a formulation of a real-world problem in mathematical terms. So that would be like Newton's law of cooling or a population model. And so we're going to have to construct that to get a math model. What we're going to do is analyze or find the solution to this mathematical problem. And then we're going to interpret the mathematical results in context to the original real-world problem. And that, by definition, is mathematical models. Alright, so there are different types of differential equations that you will run into. There are ordinary, and an ordinary differential equation is the unknown function that depends on a single variable, and insofar unknown function just depends on a single variable. It's an ordinary differential equation. The population model we talked about earlier is an ordinary differential equation. And then the other one is a partial differential equation, and that's an unknown function that depends on 2 or more independent variables. And a differential equation of that would be something that looks like this. And this is a partial differential equation. In this class, we're only going to deal with these ordinary differential equations. Partial derivative is a totally different class, usually taken after you finish differential equations. And then another class of differential equations are called initial value problems. And this consists of a differential equation with an initial condition, which would be something like this. There's our population model. To give an initial condition, I would have to know the initial population we started with at t equals 0. These two together, this differential equation and this initial value, is an initial value problem. And so this allows me to predict my solution